Hello students. In the previous section, we have studied about conductors, semiconductors, insulators and p-type material and n-type material as well as intrinsic semiconductors and extrinsic semiconductors. We have also learned that semiconductors have wide range of applications in our present day world. Our computers, laptops, TVs, audio systems, music systems, communication systems, control systems, satellites, transmitters, receivers, all use semiconductors for their functioning. Hence, semiconductors are very important. Semiconductors are also important from the point of view of board examinations, whether it is a state level or central level, NCERT, NEET or JEE entrance examination. Please don't neglect this chapter because it will help you to score more and more marks. We will continue with our lesson on semiconductors in this chapter 14 part B. Please see the diagram. Here in this diagram, a single crystal of silicon material is doped with p-type material on the left side and n-type material on the right hand side. So, there is a p-type impurity added on the left side and n-type impurity added on the right side. When such a thing happens, the current flows due to the gradient, that is the potential gradient from p-type to n-type. Hence, holes move from left side to right side and electrons move from right side to left side. This is called diffusion current, that is I diffusion. So, diffusion current is due to majority carriers. Majority carriers are holes on the p side and electrons on the n side. When these sufficient number of holes have moved towards the right side, towards the n side, and electrons have moved towards the p side because of their charge differences, because electrons are negatively charged, holes are positively. So this remains positive here and negative here. A region in the balance condition, a region called depletion region is formed. Due to this, the depletion charge, there is a positive on the right side and negative on the left side. Hence, minority carriers. Here, minority carriers are electrons. So, electrons and holes also have minority carriers. Holes are minority carriers here. They move in the opposite direction and a drift current due to minority carriers is also flows. Hence, there is a diffusion current and drift current in a PN junction. So, because this is positive, this graph is plotted here and a barrier is created here due to the charge difference between negative and positive here, and this is of the order of 0.7 volts for silicon and 0.2 volts for 0.2 volts for germanium and 0.7 volts for silicon. Whatever we had seen in the previous diagram is again represented here in this diagram. Here there is a p-type material on the left side and n-type material. Holes from p side have moved towards n side, which are holes which are positively charged, are shown here. Similarly, electrons, which are majority carriers on the n side, have moved to the towards p side. Hence, a depletion region is formed. This depletion region is shown in the white color in the diagram. So please see, there is an electron diffusion which moves from right side to left side, majority carriers, and hole diffusion from left side to right side. This is also majority carriers is shown in the red color. And similarly, the electrons are minority carriers in the p side. So they also move because of this positive potential, and their drift current also flows from right side to left side due to minority carriers and left side as shown in the blue color diagram. Consider a thin p-type silicon semiconductor wafer by adding precisely a small quantity of pentavalent impurity. That impurity part of p-type silicon wafer can be converted into n-type. Here the pentavalent impurity is added on the n side. The wafer now contains p region and n region and a metallurgical junction between p and n. The two important processes occur in the formation of a p-njunction. During the formation of p-njunction and due to concentration gradient across p and n side, holes diffuse from p side to n side and electrons diffuse from n side to p side. This motion of charge carrier gives rise to diffusion current. See here, holes from p side to n side and electrons from n side to p side. You remember this one. And this is a diffusion current. Diffusion current is shown here. Majority carriers and majority carriers. As the holes continue to diffuse, a layer of negative charge or negative space charge region. This is the negative charge on the p side of the junction is developed. Because holes have moved here, a negative charge is developed here. The space charge region on either side of the junction is known as depletion region. This is the depletion region. As electrons and holes taking part in initial movement across the junction depleted the region of free charges. They have reduced the region of the free charges. The thickness of the depletion region is of the order of 1/10 of a, it is very small, 1/10 of a micrometer. This is the depletion region. Due to the positive space charge on the n side, this positive space charge on the n side and negative space charge on the p side, an electric field directed from positive charge towards negative charge is developed. Due to this field, an electron on p side of the junction moves to the n side and a hole on the n side of the junction moves to the p side. The motion of charge carrier due to electric field is called drift. See, this is opposite. That is due to and field. This is a drift current. Okay, this is, you see here, this is a drift current due to minority carriers. Minority carriers here are a hole. Here on the n side it is a hole and p side it is an electron. Due to this field and an electron on p side and junction on p side of the junction moves to n side and hole on the n side moves to the p side. The motion of charge carriers due to this field is called drift current. Thus, a drift current which is positive in direction to the diffusion current starts. See, the drift current is opposite to the direction of diffusion current. The diffusion current is in this direction, majority carriers. Diffusion current and drift current is opposite to that. Initially, diffusion current is large and drift current is small. As the diffusion process continues, the space charge regions on the either side of the junction extends, thus increasing the field strength and hence drift current. This process continues until diffusion current equals drift current. The process of movement of holes and electrons, that is majority and minority carriers, continues till diffusion current is equal to drift current. Thus, p-n junction is formed. A p-n junction under equilibrium, in a p-n junction under equilibrium, there is no current. So, under equilibrium, please note, under equilibrium, there is no current. The loss of electrons from n region and gain of electron by the p region causes a difference of potential across the junction of two regions. The polarity of this potential is such as to oppose further flow of carriers so that a condition of equilibrium exists. The p-n junction at equilibrium and potential across the junction is shown in the figure 1. Figure 1 is given in slide number 2. Please note and refer back. The n material is thus positive and relative to p material. Since the potential tends to prevent the movement of electrons from n region to p region, it is called barrier potential. Please note, what is a barrier potential? It is nothing but the potential which prevents movement of electrons from n to p is called the barrier potential. Now, having studied the characteristics of movement of minority carriers and majority carriers, let us study about semiconductor diode. In the figure, a p-n junction is shown. This is a p-n junction. This is a p-n junction where two metallic terminals are connected. These are two metallic terminals and this is also a metallic terminal. Here this is a left side is p-type material impurity and the right side is a n junction, and the junction is called p-n junction and the center position is depletion region as we have seen in the previous slide. This junction is called a diode, semiconductor diode, and is represented as an arrow with a vertical line. This arrow type or a triangular type is a positive p side and n side is a flat vertical n side. Therefore, the whole device is called a p-n junction diode. It has two terminals, one on the left side and on the right side. Between these two terminals, we can connect a external supply voltage. Either we can connect either a positive on this side or a negative on the any of these side, and vice versa on the opposite side. A semiconductor diode is basically a p-n junction. A semiconductor diode is a p-n junction with metallic contacts provided at the ends of application of an external voltage. Between these two contacts, metallic contacts, we can connect an external voltage. It is a two-terminal device. Diode is a two-terminal device because two terminals are the metallic terminals are there. The equilibrium potential can be altered by applying an external voltage V across the diode. An external voltage can be connected. p-n junction under forward bias. Please see the junction here, an external voltage, a battery is connected here, p-n junction. This is a p and n, and this is a depletion region. So this is a positive. In the forward bias, this end is positive and opposite to that is negative. This is negative. So positive is connected to P, negative is connected to N. And when we connect this, the holes are, when an external voltage V is applied across the semiconductor diode such that P side is connected to positive terminals of the battery and N side is connected to negative terminal. See, N is connected to negative and P is connected to, P side is connected to positive. This is forward bias. P to positive, N to negative is forward bias. The direction of applied voltage V is opposite to the built-in potential V0. As a result, the depletion layer width decreases and the barrier height is reduced. This is the barrier height. This is barrier height. It is reduced. So initially it was 1 at the position 1, and when we connect it to forward bias, the barrier height is reduced. The effective barrier height under forward bias is V0. Initially it was V0 and it is reduced to V. Hence it is V0 minus V. The total diode forward current is sum of hole diffusion current and conventional current due to electron diffusion. The magnitude of this current is usually in milliamps. Under forward bias, the current is in milliamps. It is comparatively more than the reverse current. In forward bias, the current first increases slowly. The current increases slowly. You will also see in the next diagram VI characteristic, and almost negligibly, till a voltage across the diode crosses a certain value. Here, till it crosses, this value is called, and thereafter, after the characteristic voltage, the diode current increases significantly. Even for a small increase in voltage, in a small increase in the bias voltage, this voltage is called threshold. Here it is the threshold voltage. You see here, this is called threshold voltage. It is of the order of 0.2 volts for germanium and 0.7 volts for silicon. Now, having studied the forward bias, now we will reverse the battery potential as shown in the diagram. In the previous example, we had connected positive to P and negative to N. But in reverse bias, we connect opposite. That is, negative to P terminal and positive to N terminal. And in these circumstances, holes which are positively charged move to the left side, that is attracted towards battery, and electrons which are negatively charged are attracted towards the positive terminal of the battery. Hence, this depletion width increases. So under reverse bias, the depletion width increases and there is no flow of current, almost zero. In the reverse bias, the current flow is almost zero. When an external voltage V is applied across the diode such that N side is positive and P side is negative, it is called reverse bias. P side is negative. The direction of applied voltage is same as the direction of the barrier potential. The barrier potential was, see, if you had observed it, the barrier potential, it was minus here and plus here. In the previous diagram, if you go back and refer, it was minus here. The barrier potential was minus and positive plus here. So battery is also minus this side and plus on this side. You please observe this. Barrier potential is same as the applied potential. As a result, the barrier height increases. The barrier height increases and depletion region widens. The depletion region widens. Please note. The depletion region widens in the reverse bias due to the change in electric field. The effective barrier height under reverse bias is V0 plus V. This suppresses the flow of electrons from N to P because it is positive and holes from P to N. Thus, diffusion current decreases. Electrons on P side or holes on N side in their random motion come close to the junction. They will be swept to the majority zone. This drift of carrier gives rise to the drift current, which is of the order of microamps. This is also an important point to please note. It is microamps. That is, micro means 10 to the power of minus 6. Micro means 10 to the power of minus 6. Having studied a p-njunction diode in forward and reverse bias, we will plot the variation of current, whether it is a forward current or a reverse bias current, with respect to the voltage variation. Please see the graph. As we had seen in the previous example, this diode, this is a forward bias condition wherein as we increase the forward voltage, the current increases after an initial knee voltage or a threshold voltage. This is a knee voltage or a threshold voltage. So, as we increase the voltage, the current increases after initial saturation here, after knee voltage. In the reverse bias, when we increase the negative voltage in the negative direction, there is no flow of current. It is almost zero. There is no flow of current. No flow, it is zero, and till it reaches a breakdown point. At the breakdown point, the current increases enormously. Almost the device, that is the diode, is destroyed in this region. This is a reverse bias and this is a forward bias, and the entire curve plot voltage versus current. This is a forward current and this is a reverse current. Reverse current is of the order of microamps and forward current is of the order of milliamps. Please note here, forward current is milliamps and reverse current is microamps. The current under reverse bias is essentially voltage independent. Independent means it is constant up to this point, known as breakdown voltage. This is a breakdown voltage, VBR. When V is equal to VBR, the diode reverse current increases sharply. This current increases sharply. Even a slight increase in voltage, in bias voltage, large change in current appears. If the reverse current is not limited by an external circuit, below the rated value of PN junction will get destroyed. So we have to operate the diode under reverse bias in a very operating voltage that is specified by the manufacturer. For the diode in the reverse bias, the current is very small and in the order of microamps. Microamps, yeah, in the reverse bias. And almost remains constant with change in bias. It is called reverse saturation current. For diodes, we define a quantity called a dynamic resistance as the ratio of small change in voltage dV to a small change in current. You see, in this equation, we define a dynamic resistance RD, that is equal to change in small voltage delta V divided by delta I. This is applicable for both forward bias and reverse bias of a rectifier. In the figure, a transformer is shown. This is a primary winding of a transformer. This is a primary winding and this is a secondary winding. To the primary winding, if we apply an else alternating voltage, that is a full cycle of voltage. And if an alternating voltage is applied to the primary winding, and this is a diode is connected such that the top end is positive, P side is connected to the one end, and N side is connected to the load RL, that is a load. Our load can be anything, maybe a battery charger or a TD or mobile device or anything. So this is just like a battery charger. In battery charger, we connect supply voltage AC and we tap secondary. If an alternating voltage is applied across the diode in series with a load, the pulsating voltage will appear across the. See, this is the pulsating voltage applied to the primary. So when we apply this full wave during the positive half cycle here, where positive half cycle, this end becomes positive and the diode is forward bias. During when the diode is forward bias, it allows the current to pass through and the current appears across the output. This is input and this is output. At the output, we get a pulsating area, we will get an output during the positive half cycle. And during the negative half cycle, that is in this negative half cycle, there is no flow of current in the output. There is no current flow here as shown. Hence, output is also shown here in terms of a pi diagram. That is 0 to pi, there will be flow of current. Pi to 2 pi, there is no flow of current. And pi to 3 pi, there is a flow of current. And 3 pi to 4 pi, there is no flow of current. If an alternating voltage is applied across the diode in series with a load, a pulsating voltage will appear across the load only during the positive half cycle, when the diode D is forward bias. Such a rectifier is called half-wave rectifier because current is appearing only for half-wave. Please note, in half-wave rectifier, we use only one diode, a single diode is used. The secondary of a transformer supplies the desired AC voltage across the terminal when the voltage at the upper end A is positive. The diode is forward biased and it conducts. When A is negative, the diode is reverse biased. During the negative half of cycle, that is during this process, the diode is reverse biased. That is during negative, it is reverse bias and it does not conduct. Therefore, in the positive half cycle of AC, there is a current through the load resistor RL and we get an output voltage. Whereas there is no current in the negative half cycle. Since the rectified output of this circuit is only for half of input AC wave, it is called half wave rectifier because current flow is there only during half cycle. Having studied about half wave rectifier, let us see the function. Let us study the functioning of full wave rectifier. In the diagram, we have shown there are the circuit diagram of a full wave rectifier is used. In the full wave rectifier, two diodes are used. These diodes are D1 and D2 connected as shown in the figure. This is a transformer and the longer is this is the primary winding of a transformer and this is a secondary winding. In the primary winding, we have a full wave input, AC input, and the secondary is shown as during positive half of cycle, and the center point, the load is connected at the center point. Please note, the load is connected. This is the center point of the transformer. Upper end is connected to diode D1 and lower end is connected to D2. And center point is connected to the load AB as shown in the diagram. The circuit using two diodes is shown in the figure, which gives output of the rectified voltage corresponding to both positive and negative half of cycle. Hence, here the output voltage appears for both positive and negative half of cycles, and this is called full wave rectifier. Here the P side of one of the diode is connected to the top and top as well as the bottom points of the transformer, positive and negative points of the center tap transformer. The N side of the diodes are connected. This is the N side of the diode and the D1, and this is the N side of the diode connected to the both N sides are connected together, and one end is connected to the load. AB is the load, one end, and the other end of the load is connected to the center point. This is the center point. Suppose the input voltage of the upper end is positive. If this end is positive, correspondingly this side will be negative. Hence, when the positive end is D1 is forward bias. When this is positive, D1 is forward bias, and the current flows in the secondary in this circuit. From B to A, it conducts. When this is positive, current flows in the upper half. In the next cycle, when in the negative cycle, what happens? In the negative cycle, this becomes negative and this becomes positive. When this is positive, D2 will conduct, and D2 and current will flow like this from this to this and to the center tap. Hence, current flows for both positive of cycle through the upper part and through the negative cycle, it flows in the negative part. Please note, current flows from B to A and to the center tap. When the voltage at the top end becomes negative, the current flows. Thus, we get an output voltage during both positive cycle as well as the negative half of the cycle. These are the diagrams. This is the input. This is the input voltage applied across the primary of the transformer. 0 to 2 pi is one cycle. This is a positive cycle where D1 conducts, and in the negative part D2 conducts. The output voltage appears as a pulsating voltage. It is, you see, it is in the form of a sinusoidal wave output. But in some circuits, we need to be a flat DC voltage. Instead of pulsating output, we want a span, for which we use filters. Filters for rectifiers. Full wave rectifiers are more efficient circuits for getting rectified voltage or current than half wave rectifier. That means efficiency. Full wave rectifiers have the efficiency. Full wave rectifiers are more efficient circuits. The rectified voltage is in the form of pulses of the shape of sinusoidal wave. To get the steady DC output from pulsating voltage, normally a capacitor is connected. A filter is nothing but a capacitor across the output terminals. It can even be an inductor in series with a resistor. Hence, the filter can be either a capacitor connected across the output terminals, that is across RL, load resistance, or an inductor in series with the load resistance RL. Hence, it converts the pulsating DC to a smooth DC. That means filter is a smoothing circuit. With this, we come to the end of part B of chapter 14. And next part, we will study about the special electronic devices. Thank you.